Welcome to a new video about LC ladder filter design. This is our example considering the Chebyshev response for a low pass filter. We will discuss the fourth order filter, which is an even order filter, and we will see that we will use an unmatched source and a load. So the source resistor will be not equal to the load resistor. We have done this for the Chebyshev response for the third order. Now we will do that for the higher order, which is the fourth order. So we will see that step by step in our calculation, also verify this in Tina TI SPICE simulations. Okay, our design objective is the following. We need to have a Chebyshev response passive LC ladder filter configuration for a low pass filter. The final design has a source resistor 200 ohms and the load resistor must be 25 ohms. The specifications are shown here for our filter. We need to have a maximum passband ripple 1 dB. Again, this is a 1 dB ripple Chebyshev response. The minimum stopband attenuation required is 30 dB. The passband frequency is 1 MHz. That means at this frequency we will have the maximum ripple of 1 dB. And the stopband frequency is 2 MHz. That means again at this frequency 2 MHz we need to have an attenuation at least 30 dB. Okay, let's see how we can create this, design this filter. The solutions. We start first with the filter order calculation and we relate the A max and A minimum here to the epsilon P and epsilon S. So first the scalar value epsilon P connected to the A max. So just substitute here the A max of 1 dB. So you get now 0.5088. In a similar form for the epsilon S for the stop band attenuation value, which is 30. So we substitute that here, we get now a 31.607. Taking this together in a similar form we have done for the Chebyshev response in the previous examples, we can use this formula and then substitute the values here. We see here the Fs and Fp, which is then 2 MHz over the 1 MHz. And these are the values we just determined here, and that will result in 3.6615. That means we need to go to an integer value, so we need to have an NS4, so we need to have a fourth order filter. So we need to look at the table of the Chebyshev response 1 dB ripple for the fourth order system for the LC ladder low pass filter. So we have normalized element values. In the first column you see here the RS over RL. This is the ratio of the source resistor and the load resistor. In this case we have 3 and 4 and 8, so different values and also infinite. X1, X2 and X3, X4 are the normalized element values. So this is the capacitor, inductor, capacitor, inductor. So we have here 2 capacitors and 2 inductors. These are all normalized values. If you look at our specification, we see that the RS over RL, so 200 ohms over 25 ohms will be 8. So we need to look at this row, which has then these normalized values. So that means following. We first start with the frequency scaling factor, KF, which is also the cutoff frequency. And then we will use these values in the actual scaled up component values. Now the KF, which is the scaling factor for the frequency, is given by this formula. You see here again the omega p, which is the 2 pi times the fp. And then this part, which is then the cosine hyperbolicus with this argument in order to convert this passband frequency to the cutoff frequency. You see that we have an N, which is the filter order 4, epsilon S, epsilon P, which is then this value. So when you substitute that in here, you get here 6.616 million radians per second. This is now the actual cutoff frequency of this circuit in radians per second. Okay, now step 3 is the scaled component values. This is the fourth order low pass filter normalized elements. You see here again the RS and RL and the 4 reactive components. This is the C1, L2, C3, L4. So what we see here, the 0.2085 farads is for C1 in the normalized value. For L2 we have this one, for C3 we have this one, and for L4 we have this one. So this is actually how we read it. In the normalized value, the RL will be 1 ohm and the RS will be, in this case, 8 ohms. So we have 8 over 1. That's actually showing. So always normalize your load to 1 ohm and your source will be then related to that in the same fashion. So we go from here to here. You see all the primes here. You see here the RS prime, etc. That will be then scaled up values for the components. So it means the following: C1 will be scaled up to C1 prime, and this is the formula. You see here the Km, the magnitude scaling factor, and the Kf, which is determined in step 2. Why is this Km 25? Because we need to go from the normalized value of the load of 1 ohm to 25 ohm, which is our final design. That's why we have the Km of 25. And the frequency scaling factor is already determined in step 2 as set. So we also take this 0.2085 from the table, and we calculate here the required component value for C1 prime, which is the 1.261 nanofarads. And for the inductor, we use this formula. So we have now the Km in the numerator, and they use also the scaled normalized value from this column, x2, and then calculate this again using the frequency scaling factor. Get now here 64.86 microhenries. Now C3 is similar to the C1, so use now this normalized value. You get now here 2.585 nanofarads, and L4 is similar to the L2. In this case, you get now 12.40 microhenries. So the RS scaled up will be then 25 times the RS we have here, which is then 8. That will be then 200. And RL prime will be then 25 times 1 will be then 25 ohms. So we have now all 6 values for our filter in the final design. So our design circuit is shown here. This is the normalized version. You see also the values here from this row. 8 ohm as said before, and for the load is 1 ohm, so the source and the load. And you see here all the scaled up values we just determined. Okay. Let's now look at the simulation results. This is the Bode plot for this circuit we just determined, all the values. So we actually plot the Bode plot for this circuit, fourth order Chebyshev response having 1 dB ripple. You see the low frequency or the passband gain here, which is minus 19.085 dB or 1/9. Why is this correct? Now in the low frequencies or the passband frequency, the capacitors are all open and the inductors are all shorted. That means we have then RL over RS plus RL. This is just gain. And that is looking at the values, which is then 25 over 200 plus 25, which is then 1/9 actually. So you do actually 20 log of the 1/9. So you get minus 19.085 dB. So this is indeed as expected. We also see here the cutoff frequency, which we have calculated that as 6.616 megaradians per second. If you convert that to hertz, you get here 1.095 megahertz. It is almost 0.1 megahertz, so actually in this case 95 kilohertz larger than the passband frequency. What you also see here is the stop band attenuation. Now the baseline here, as you can see here, so the low frequency gain is minus 19.085 dB, and at 2 megahertz we have a gain of minus 51.96 dB. So how far do we go down? Now that's calculated using here the just difference. So you get now 32.875 dB, but we required minimum 30 dB. So this is indeed as we have wanted. So this is also achieved. And the final one is the passband frequency. Looking at 1 megahertz, you see here the gain is minus 19.089 dB. You might say, then how is this work? Because this starts there and then you come at almost the exact same point. That's actually the characteristic of an even ordered Chebyshev response. You start actually at the lowest value and then make a peak. And go down to the valley, make again a peak, and then come at the point where you started here at low frequency gain. So we have here now almost 19 point as the passband gain here. So this is also as expected. Okay, now that means we have all checked the values according to the specification for this filter. Now let's also give the Chebyshev response 1 dB ripple table. These are the normalized values from NS2 up to NS7, so the second order up to 7th order. You see also here the ratios of the load and the source, and also the X1 up to X7 for the normalized element values. And these are the filter circuits, 2nd and 3rd order, 4th order, 5th order, 6th order, and the 7th order. Alright, this was our example considering the 4th order Chebyshev response having a 1 dB ripple, using the LC ladder filter configuration. If you have any questions, comments, please let me know. I will try to answer them as soon as possible. See you next time in another video.